Welcome to Season 8 of the Prosthetics and Orthotics Podcast. This is where we chat with experts in the field, patients who use these devices, physical therapists, and the vendors who make it all happen. Our goal? To share stories, tips, and insights that ultimately help our patients get the best possible outcomes. Tune in and join the conversation. We are thrilled you are here and hope it is the highlight of your day.
Hello everyone, my name is Joris, and this is another edition of the Prosthetics and Orthotics Podcast with Brent Wright. How you doing, Brent?
Hey, Joris, I'm doing well, man. Hey, we're inching up closer to that 100th episode.
Oh wow, dude! I still cannot believe that we got this far with this session, to be honest.
Well, and congratulations to you on the 200th episode of the 3D Pod. I mean, how cool is that?
Yeah. Exactly. I think I've now got a total like 300 podcasts in my belt. I think I should get some hipster medal or something like that. I think if I do 400 podcast episodes, they have an apartment waiting for me in Brooklyn.
It's in lower Brooklyn. If you do SoundCloud, you'll be in Bushwick or Williamsburg. If you do a podcast, it's down Oxford.
Okay. Thank you. Well, thank you for the hipster advice there. That's from Duann Scott. Usually the whole conceit of this podcast is that we don't know. I don't know the guest, right? And then, but this case, I do know the guest. And so Duann is. We kind of have a little overlap with Shapeways together and stuff, and then we've bumped into each other lots and lots of times in 3D printing since then. And Duann now is head of the 3MF Consortium. This is like a group of people that are making a standard for 3D printing files that is hopefully better than the STL. And he's doing some consulting stuff. He's doing some stuff for MIT. He's doing lots of exciting stuff. And he's essentially like kind of like a software DFAM guru. He's done some amazing stuff on the software front. So it's awesome to have Duann here today.
Thanks for having me.
And so for the show, first off, we have a sponsor, right? It's called Advanced 3D. Do you know anything more about Advanced 3D?
Well, yes, Advanced 3D. I'm involved in it, and along with Paul and Tyler, and we focus on the orthotic and prosthetic field to really get people up and going and 3D printing. So the idea is we meet you where you are, whether you've never scanned a thing in your life or you're scanning and you're doing some design, but you want to maybe go into the definitive prosthetic or orthotic device manufacturing. We can help with that. And so, and it's really neat to see all this stuff coming into play, especially with some of the stuff like what you've talked about, and we really are fans of. There are these flexible TPU style devices that actually move and move with the patient.
Okay, that's super cool, dude. That's super, super nice.
How do you know Duann, Brent? Like, this is like the thing.
Yeah, I mean, so we actually have known each other for quite a while, probably 2017, 2018. I think we connected at a show, and he's like, you really need to start looking at some computational design stuff. I didn't even know what he was talking about. And stuff back then was a little bit rough, and I was like, man, it is over my head. But we've stayed in contact over the years, and we've actually had now some overlap on some things, and we've connected at shows and such. But I just appreciate what he's doing, specifically not only trying to get share the difference between AI and what computational design is, right? But then also the 3MF Consortium. And I think this is where things get really interesting for O&P, and why it's so important is because STLs do not have units of measurement. So when you bring,
time I found that out, I was like, "You've got to be kidding!"
Well, and we run into this all the time. Like we get files, standard, metric, and depending on, is it a U.S. based company and or do they have headquarters somewhere else? And so you think that you're printing the right thing, and as a contract manufacturer, you think you're printing the right thing, and it's just a complete disaster. But then, so that's one benefit of the 3MF, but the other benefit is that it also holds the color and textures in one file. So like if you with an OBJ, you usually have your color file and a texture file. And so you've got these three files that are kind of trying to float along together. And for us, when we're printing color, it's just super important that it's all together in one file, because so many times it can break. And the 3MF file's smaller too. So, I mean, there's a big benefit to us. And I don't know all the ins and outs, so I'm looking forward to hearing some of that. But just from my, mountain North Carolina boy perspective, those are a lot of the benefits of the 3MF. So, and I appreciate Duann, really leaning heavily into that, and it's gaining steam. So I'm really excited about that.
Yeah, it is getting wider adoption. And just to be clear, I do nothing technical for 3MF. I just help people understand where and how they can use it. More like, and then the consortium is a number of engineers from all the major software and hardware companies who come together in a very unique, non-political way to figure out ways to share data between different software and hardware systems. So I think it helps a lot. So as you said, the STL has no idea about scale. So you could be doing millimeters, inches, meters, kilometers, miles, yards, yardlings, whatever else, and no color, no metadata. So it's a problematic file format that worked well for the first couple of years of rapid prototyping, but it's not really made for production. And so the 3MF format is a manufacturing file format in that you can carry all the metadata required for both the information about, say, your client, the manufacturing process, as well as the geometry itself. So a lot more information there than just dumb geometry, which is what's important.
Okay, and you give some examples of this, because I think a lot of people don't appreciate just how important it is to move away to something that works a little bit better. What can I put in this file format? I can put a lot more information about the author, for example, right, or the materials, all sorts of stuff, right?
So it's an open source file format. So we have standards that all the software companies have agreed to, but you can put anything you need in there. So you're limited by what the authoring software enables. So what you can do in Fusion 360 versus what you can do with Rhino is different, but they will read each other's data. So with Rhino, you can put in the author information, copyright information, date, all that kind of stuff. And with Fusion, you can do that if you're in the manufacturing format. So it depends on the software, but it's open to anything, but the default is geometry, author, scale, material, those kind of things. We also have extensions for other capabilities. So if you're looking to do something like lattice structures, we have a beam extension, which you can then describe the lattice structure as a series of beams instead of a mesh geometry, which means a file size might be, I've done a full build of an EOS machine, which was something like 1.2 gigabytes, was down to 165 kilobytes. So a massive reduction in file size by just describing the graph, not the skin of the object. So there's a lot of benefits.
Okay. And then and the 3MF consortium itself, it's it's open source. How is it open source? How do I know it's going to stay open source? That kind of thing. And how do I know you're the right people to gather our interest, if you will?
So it was originally started, I think, in 2016 by Microsoft, when they were looking to get into the consumer printing space and seeing that the STL file format was, their data people. So they saw the STL format was not a functioning way to go forward. So they looked at AMF, which was already under development from some academics that had some interesting ideas but had no industry buy-in. And so they developed the 3MF format and brought together all the major CAD companies. All the major CAD companies came together because they had FOMO of missing out of, doing business with Microsoft. And so all the major companies came together. We're under the Linux Foundation, so it's the whole entire structure is open source. It can never be closed source. And we're currently in the process of going through ISO certification as well, so it'll become like an industry standard. So there's no chance of us closing things off. It's a non-for-profit, so no one's making any money out of this. The file format's accessible to anybody. The steering members all pay to be steering members, so they can pay for the testing and analysis we do. So we ensure that it works in every possible iteration we can think of or we can find. But everything's open and always will be. You can go to the GitHub and access the code now and start using it. So a lot of hardware and software companies use it as a default transport for their geometry and the build. So people like Ultimaker, Prusa, and Bamboo Labs all use the 3MF file format, not just for the geometry for part level, but also for the entire build. So the machine material combinations are all in that file as well. And anybody can do the same thing. They can take the existing data format we have and add functionality. So that's the production extension. Others do that as well.
Yeah.
People like Desktop Metal and HP also do this on the industrial level.
So there's actually an advantage, right, to using a transport, because maybe people don't realize that. Well, a lot of these file types are not really great at describing the object because they cut it into lots of little triangles, and these triangles are a little different. And you could do this in different ways, even in the CAD software, right? So if I'm take a CAD program and I'm changing it to your CAD program, or if I'm changing it to a G code, there all sorts of stuff can go wrong, right?
Yeah. So the CAD companies use different formats so they can keep you in their little walled garden. And then only when you need to send it out to another system to manufacture do they sort of allow it to go out. There's been step interchange for years in CAD. One of the issues that comes up is that the geometries we're creating for 3D printing are often more complex than CAD systems can sometimes represent in a proper way. So when you're doing a complex geometry in CAD, what you see may look like a solid object, but what's happening with all those surfaces is sometimes they don't properly connect. And so when you export that as a STL mesh file, there's gaps or there's reverses in the triangles, boring stuff that means that your print won't work properly and you need to go in and repair that mesh file, which is time consuming and means that you can't automate the process. If you have to go in manually and repair things every single time, then you can't just make a stream and run it and have someone just like input information. You have to then go through and make sure every step of the way everything's being okay. So things can't scale to be profitable when you have to manually intervene every time you make something. So the idea with the 3MF file format is that it has a more elegant way of communicating the triangles as a basic mesh to start off with. So the mesh is always watertight, which means you don't have to go and repair the file theoretically. And if you're doing a more complex geometry, like I mentioned with the beam lattices, you can communicate it as beams and nodes rather than the mesh, which means it's much more efficient and you don't have to mesh it to slice it and to print it. And then we have other formats like the volumetric, which can give you voxel by voxel information if you're doing a full color print or a multi-material print. So there's just so much more data you can encapsulate in a smaller file size, which is usually more reliable.
Okay. And I think this is only going to explode, of course, as we go into more voxel-driven processes, where we'll be able to, change more properties at the local level. But also, hey, you talked about these lattices. If we have a really complicated structure with lots and lots of lattices, that file size is going to be huge, and it's going to be unwieldy, and it's going to crash my computer a lot. And now with 3MF, that's going to be much more manageable for the individual user as well, right?
Yeah, that's right. Yeah, so it saves time and space. So if you're the typical file size for a 3MF versus an STL file is 1/3 the size if it's just pure mesh. If you go to the lattice structures or the volumetric, then you can have as I said, something that was a gigabyte can be down to kilobytes. So sometimes, and then if we go to the implicit representation, which we're also working on, the file size can be smaller than a screenshot of the image. So we can really that's with pure implicit. So we can get the file size down to very, very minimal when it's a pure mathematic function. And it's just a much more elegant way of describing not only the geometry, but what's happening inside. So, when we first think of 3D printing, it's like a monolithic volume where we use the same materials and same parameters throughout the whole thing. But if we are doing a more elegant design, perhaps we'll have different properties within a part, either by multi-material or changing parameters. So if you're using a machine where you can control the parameters to at the voxel level, you can design for that as well. So we can change the porosity of an object or its energy absorption or its mass distribution just by changing the density of the material using parameters. And you can sort of design that into the part. And this is for the more advanced designers for now, but I think it will become more normalized as the tools become easy to use to do this sort of volumetric design.
One thing that I was always curious on, especially with the 3MF, and I know we've talked about it, on this and then for other companies, but does the 3MF road also include like security or some sort of encryption of your file, so it can't be used, like if it gets out or whatever. So I'm always curious about that part, because I think I shared, I've had 2 parts that were unauthorized showing and printing recently happen, and I was like, man, how can I avoid that?
There is a security extension to 3MF. So 3MF has a core spec, which is a mesh file in a zip. So it's smaller and smaller because it's zipped as well. And then there's extensions for different functionality, such as the beam, the color, volumetric, and the security is another extension. So if you enable that in your workflow, you can restrict who can access that file, how many times they can print it, what machine it's printable on, like down to the serial number of the part of the machine if you want. Or you can say only this person can use this password, or only someone can use it this many times. So there is functionality in there, and the reason we did that is because there were in the sort of like the hype days, there was probably like 10 or 15 startups claiming to have some sort of security for 3D printing, all of which were kind of didn't exist, because unless you have access to the machine, like to the data of what's driving the machine, you can't really do security. So 3MF, if the machine and software has that enabled, then you can do that. If the machine and software does not, then you can restrict it by a password, and then that's sort of your best bet you've got.
All right, we're going to pause right there, and we'll get back to Duann in a minute. I wanted to introduce to you a new sponsor, and that sponsor is LimGuard. LimGuard has a myriad of products revolving around postoperative care for patients. And one of the neat things, I think, about the LimGuard is that not only does it come with the protector, it comes with a suspension sleeve, and it can come with 3 limb socks that are one size fits all. And if you are a clinician or a clinic, you only need to stock 4 sizes that are left and right compatible. You can also add your logo and your clinic logo so you can follow up with those patients throughout their care, and after they get out of the hospital, they know who delivered the protector to them. It's great for the patients, provides protection. It's great for you. You get to be in front of the patients early in their care. And in the end, it's just a better outcome. So special thanks to LimGuard for sponsoring this episode. And now let's get back to Duann. Wow, that's pretty cool. Yeah, I'll definitely have to look into that side of things. And I think that's interesting, especially when you're starting to get into some of the manufacturing and even dialing it down into the serial numbers of the machines and such. That's pretty neat. I can see why you get excited about this kind of stuff.
Yeah, I just think it's necessary. So we have to do the work to make it so it's normalized and available to everybody, and it becomes standard. A lot of the 3D printing industry has just had a prototyping mentality for a long time and just kind of glossed over some of the technical issues about data communication and making sure it's scalable. And so while the machines and materials have improved considerably over the last, I'm going to say 6 years, the data flow needs to also mature as the design tools have as well. So we're at the stage now where it's time to sort of grow up and get our shit together and do things properly, rather than just sort of hacking at things, which has happened for the past 25 years.
Right. And I'm super curious, the lattice structure thing is very interesting in the 3MF because I do a lot of that. But Can you share a little bit about what the difference between that aspect and the implicit is for our audience? I mean, I know that implicit files are smaller and it's a mathematical formula, but that's about as far as my knowledge goes, right? Yeah. So can you explain that to us?
Sure. So so lattice structures sort of come in 2 flavors. There's a beam-based lattice, which is a series of like rods which interconnect. They can have varying thickness, and typically there's a single profile for all of them, which is a rod. So when we communicate a lattice structure that's a beam-based one, we can do it as a series of cones with a diameter and endpoint being a sphere or a cutoff. And so when you're designing a lattice structure like that, you can describe that as a graph. When you're doing a TPMS, which is a triply periodic minimal surface, like you see the gyroids, you can't describe that as a series of beams because it's a continuous surface. And you typically can't describe it in CAD software because the amount of surfaces required to do multiple cells blows up the capability of the CAD kernel. And so to describe those geometries, we're typically seeing people use an implicit function, which is a pure mathematic representation. So you can describe a gyroid as a given formula, which some sort of sine, cosine thing. I don't really do math. And then you can propagate that throughout space and vary it. And so those are really, to mathematicians, simple mathematic equations which describe what's happening in space with a pure mathematic function. So you don't describe the surface, you describe where things are and are not. It's a weird kind of math thing. But it means you can do very, very complex forms which are irregular and not beam-based very efficiently in the sort of area of kilobytes. For like if you're doing a prosthetic, you could do if you design the whole thing using implicits, it could be like 260 kilobytes for the whole thing with variable lattice structures inside of it and different varying thicknesses of skin. But the implicit modeling process is not intuitive in the same way that CAD has become, because you are using equations to make the objects. You're not sort of drawing lines and extruding and putting bevels and chamfers on stuff. You're using mathematic equations to change the way something performs. So it's a different mindset to approach it, and it's not for everything. Like everything you see around you should not be designed with implicits or lattice structures. But for those things that need to be, it's a very, very efficient and powerful way to make things with very, very complex geometry. And because it's a mathematic equation, it's programmable. So once you've designed the formula, I'm going to call it, which is the program which makes the geometry using these equations, when you make a change to that formula, when you have a different input, say a different size prosthesis or anything, really, you can just modify that number, those parameters, and then the program will run again and you'll get your geometry again. And typically it works every time without the need for manual intervention if the program is set up right. So it can be a very efficient way to do variation and complexity. And then when you get that end geometry, if you have to mesh it, it can be very, very painful and problematic because the geometry is so complex. And so that's why at 3MF we're pushing towards this implicit representation to go straight to the machine, so we can bypass the meshing process, which discretizes the geometry down to a series of triangles, which can be time-consuming, expensive, and room for error. So anytime you change the format of the geometry, you're introducing some, you have to leave out some information, which can be problematic.
Well, I think that's super cool. Like being able to go straight to the machine. I can't tell you how painful it is, like especially with the machines that slice on the machine itself. You're not talking about a supercomputer doing these calculations. You're talking something not great. And so sometimes if you've got some bigger files, I mean, you're just waiting a while for the machine. The machine's not running until this thing crunches through the data. So I love that. Being able to go implicit all the way through.
Yeah, and theoretically with the implicit, you can stream the slices. So when you are slicing a mesh file, for whatever reason, they need to slice the entire thing in its entirety and then take that slice stack and apply it to their printing process. With the implicit function, you can query just a section of the part at a time, so a single slice, and then prepare that and process it. So you could be sort of streaming the cross-section geometry to the machine without that need to wait.
That's not good for sales, though, is it? I mean,
as long as they're selling materials, it's great.
Yeah, but what I like about this is like really instead of doing now everyone's like being the architect and you're being the builder and you're the bricklayer, let's say in CAD. And now you really see that how this could really separate out the concerns. Like Duann could be the super mesh genius guy, whatever, and he'll figure out all the force and stuff. And he could do a part of this architecture, and he can give it to Brent, who's the super prosthetics guy, who can just make it all for prosthetics. And I could just like literally kind of push in some numbers and get a good result. It'll be like a kind of like a system that makes, rather than it being a a file that we have to make unique every single time.
Yeah, and this is what's really critical that I think that hasn't come across in product design or engineering yet as much as I think it should, is this systems level approach. So when I went through university and my peers, we learned how to design a product, a thing, an object, and then we did it up until the deadline, and then it was complete. And then if we need to design something else, we started again. Maybe we use some components from the previous design to do an iteration. But if we train people to design the systems, like you're saying, where different inputs have different effects and we can trade them off, like a multi-objective optimization, then we have this more robust system. And then what we're designing is a system, and the result is some geometry as a byproduct of it. But the effort goes into developing the system. Now, we see this in architecture. So architects have been learning how to use Rhino and Grasshopper for the past 10 years in college. And so obviously their projects are very expensive and time-consuming, and there's lots of stakeholders. But what it's meant is they've developed this systems thinking and built the tools to build systems to achieve solutions. Because there's someone who's working on the facade, someone who's working on the HVAC, someone who's working on the plumbing, and they all have inputs. And so they build these software systems which plug into Grasshopper and Rhino, so they can each iterate, and then the model changes because the system's sort of alive and variable. And then once they sort of start to see everyone's requirements, they can then say, okay, this is more important here, this is more important there. And then the geometry and the entire structure of the architecture sort of evolves to meet those requirements as they shift. And if suddenly someone says, oh no, we've lost the backing of this stakeholder, we have to shift out to a different supplier, then they input their data, and then the building modifies. In engineering, it's not always as complex as that. But if we think of it in the same way, then we have this flexibility to deal with change and variability. That is one of the promises of 3D printing, and obviously in prosthetics, is that each one has to be unique. So if you design a workflow which has this variability in place, you're not manually designing each person's prosthetic. You're building the system so that it can then become a resultant part. And that way it's scalable and repeatable, and you embed the expertise into that workflow so that someone with less expertise can come in and still be, of value and help you out without having to learn everything from scratch.
I think that's super powerful. Yeah. That's super powerful. It's actually really funny because we're doing kind of something similar. So I'm working on like as a side gig kind of thing on slides, essentially recovering slides. So we asked Brent to help us, and Brent designed like gave us one to kind of as a starting thing. And then we went to a guy and he essentially designed a system for us to design unlimited slippers or slides, right?
Yeah.
So that basically is his particular genius. And now we're going to another guy who's going to help us put in the constraints for when it's too big or too small or too heavy or it doesn't work right.
Yeah.
And the idea then is that my girlfriend and I can then ultimately forever play around with these slides and change the nodes and change the struts and change the shape and the curves of things, and just say, until we get something that we like.
Yeah.
And if we were to have a slide company, if you will, if we just wanted to change a new model, it would just be like, it would take us a few minutes. So I think that to me is super powerful. I love that so much because it's a very, very different way of thinking about making stuff.
Yeah. And so when you build that workflow, you put in the constraints, which, if you would say Nike or Adidas, you would ensure that it remains on brand and functional. And so these are all constraints which you put into so if you have, a mass customization portal where you can then have anyone come in and do their own thing and modify it, you can still keep it within your own given brand and everything's fine. So it's a different way of approaching these things. And then similarly, you could pass on a workflow to someone who's an expert in a different field, who then can say, I need it to have this and this functionality. The next step is having sort of like a data input, as in sort of like you could have for your slides, you could have somebody's mass and the average temperature of the place they're going to be walking, so that the this is obviously an insane example. So you could have the slides manufactured in the right material for that terrain, and then that person's mass to see it's going to last for a X period of time. And so the data input isn't just a size; it's a like an energy input. And obviously, again, this is a dumb example, but you take this.
No, but you could ask a person to do like a test to jump up and down and see how comfortable they found it. And then you can make a level of comfort or injury return for that individual. I think that's really interesting. Or if what I like this example I use is like, imagine you had a postman or like a UPS guy who spends a lot of time in the car. He'd have a different shoe than the postman who spends a lot of time walking and doesn't have a car. And they would have a different shoe than a cop, maybe. You know what I mean? So even if they're basically the same thing, you would like to customize energy return and the comfort and kind of a lot of things to the application or the movement the person's doing.
Yeah, we already see this happening in NFL helmet design. So apparently we can't stop people hitting their heads together really hard for sport, but we can control how much they hurt themselves with some sort of energy absorption in the helmet, and we can have different helmets for different positions. So I know nothing about the sport, so I'm going to make stuff up. So if someone's a certain position, they're tackled from the side, so they need more twist reinforcement from the side. If someone's getting head-on tackled, then they need more padding to the back of their heads. So we can tune a lattice structure, which and then tunes material performance, then tunes the performance for the person receiving it through a series of equations in this workflow as well. So it's not just about fit, comfort, but also about the dangers that they're under in the given role.
Yeah, and one of the things I think is really exciting about the helmet challenge, which I think is applicable to prosthetics as well and other things, is that we can optimize that structure. Usually it's a uniform foam. We can optimize the structure for different parts of your head. Like if it's on your ears, it needs to be softer, I don't know, whatever. But what we can also do is say, hey, the most dangerous impact is some super gigantic heavy dude falling on you, or for you to hit something really sharp, right? The side of somebody's shoe or whatever, the side of a helmet. That's the most dangerous thing. So we can optimize this one structure for both those really dangerous impacts, right? And so the same thing you could do with prosthetics. You could also say, hey, we want to optimize this one liner, for example, for heavy impacts and that kind of continual impact. They're the two things that will wear down your skeletal system the most, for example. So I like that thinking because that's something that I don't think we did. We don't think like that right now. You just have a foam, put foam on it. How much foam? 2 inches. Okay.
And so there's a lot of ladder structures, like between the TPMS, these implicits, and the beam based. There's a lot of options out there, and there's about 3 people who know when to use what. It's too complex, and there's a bunch of PhDs doing work to basically allow us to inverse design. So we don't say, I want X ladder structure with X strut size at this spacing with this, cell variance. You say, I want this performance in this area, and then the software should then give you that geometry and material combination to have that role. So this is work people have to do now to feed these systems, and Carbon has done it, General Lattice has done it, and in these narrow bounds, because they control the software, the hardware, and the geometry to a certain level. It's one of the small areas where machine learning is currently working in additive manufacturing, because you can imply performance within a given constraint. So they're not exploring outside of the known, they're doing tests and then interpolating between those to get their resultant inverse design. So you can go to Carbon and say, I need this level of energy absorption in this much space, and they can give you a resultant geometry and material combination to achieve that in theory. And it's the place we need to go.
Exactly. Because I think somebody who wrote one of the books on TPMS lattices, which I tried to read for a while at least, said at one point that it gets really complicated really fast. I like Duann, do not do math. It's not good for anyone if I do that. And I've actually used mathematics once. Once to calculate the volume of a cylinder in my career so far. So trying to avoid that. So Mr. Lieberman, you were wrong. We do not need math. Anyway, but anyway, that guy said that the problem with like lattices, of course, it's kind of like it's like throwing wet spaghetti at a wall. You don't exactly know where it's all going to get, and it's all going to collapse in a kind of novel way, right? If it's under a lot of pressure, a lot of stress, or different forces.
And the machine material combination has a massive difference, and there's fatigue over time. So the day your beautiful part comes out of the machine, you've got the perfect parameters with the lowest layer height possible, so you've got the most beautiful densification, is maybe great, but then after 3 days of use, it's going to be a different material. So we are, we're indicative in the location of how things go, but perfection is not our friend yet.
No, totally not. And we have a problem as well that certain the performance of certain 3D printed materials degrades, like the young modulus degrades over time. So then with certain materials, so then we just don't get a very accurate kind of rendition of any kind of force because we don't even know what's going to happen, to be honest.
And the materials by default are typically anisotropic in that the Z is very different than the XY. So that doesn't come into play in most simulation software. So even simulating this you need to test it to get something close. And then, the machines are maturing over time, but the variance between 15 machines sitting next to each other is considerable still. So until we have some feedback loops to make sure that what you print, what you send to the machine is the same everywhere, there's still variability.
Yeah, now we're showing the slides. We're at the step now where we're going to have to print out 50 of them and wear them.
Yeah.
I'm like, but that wasn't the idea. We were going to do this all automated. This is going to be the future. And I'm like, 50? That's expensive.
Yeah.
So that's going to be fun. But anyway, so that's interesting. But okay, so now I think if you're really into this nerdiness of the size, I think you've got your fill. But like, imagine I'm somebody. We've got a lot of readers or listeners that are like, kind of like in the cusp of going into additive and looking at these file types and the software. Where do I play? What do I, do I dive deep into CAD? Do I have to learn CAD? Do I spend 2,000 hours learning AutoCAD or Fusion? Where do I play if I'm just, I just want to do my job, right? If, somebody's listening to this, she's a prosthetist, she wants to do her job. What does she need to know in order to really harness this technology? What would you recommend?
I recommend speaking to an expert first before you take a decision about how you approach it. If you just go headlong, the people who did this first had to just go in and break things until something kind of worked, and then mash it together and string together software in elegant ways to make things work. People like Brent have done a lot of hard work over the years. It's best to consult them to see what a workflow might work, and then see if there's some existing tools that they recommend. So I think that's the best advice I can give, is to ask help early on. If you just, you can do some experiments yourself in software, but I think there's so many options that it's easy to go down a wrong path and waste a lot of time if you don't take others' advice.
I think it's an interesting take. And I think, I would say, and I appreciate the endorsement there, but I would say, like, for me, it's important to surround myself with people like Duann and others that are in the space, because I am not naturally I enjoy the engineering side. I'm not an engineer. I enjoy the design side of things. I'm not a quote unquote CAD designer, but I think one of the things for me when I would answer that same question, I like how Duann answered it, was seek them out and get some information. And one of the first questions that I typically will ask is, what does somebody like an expert think about this? And you get a lot of feedback on the way they answer it. Do they go straight negative? Or do they actually have a thoughtful response of like, hey, that's a good idea. I don't know if it would work. My experience is in this, but that's very interesting. And I think that's how you can tell a true expert, especially in the additive side, because there are so many unknowns, and you want to keep an open mind, have your expertise, but you never want to down something because it may actually work at some time.
Yeah, things change. There's physics involved, so they can only change so fast and so far, but things have changed a lot over the past 5 years. 5 years has been a big difference in the software that's available and the reliability of the machines and the quality of the materials has been a massive change. So if anyone says it's never going to work, they have no imagination and they're thinking about the past. If someone says it's going to be hard, it might be hard, but I think especially for prosthetics. So that when in the early days of 3D printing, when I was looking at like what would make sense, I'd say something which is small, expensive, and custom. Now the cost of machines materials has let up considerably. If you're using a desktop FTM machine, you can get something for $400, which can do a lot, and the materials are down for $10 a kilogram. So it's not dirt cheap, but it's still pretty cheap. So the small isn't as important as it was before, and the very expensive part that I would usually recommend isn't quite so much, as the amortization of the cost of machines materials is getting lower and lower. But the custom is what's interesting here, and there's I don't know of any other way that can make an agile product like additive manufacturing. So if you're doing custom work, there's a pretty good chance that there's a way that some part of it, whether it's in the component itself or in the tooling to make the thing, like you don't want to have a 3D printed component, but you can make a tool out of a 3D printed mold and then make the component, and it's going to be better material properties and more reliable, but you just have this destructive process where you need to make a mold, which you destroy to make the part. It's still a valid way to make things. So I think it's good not to get hung up on today's technology, but the agility that it gives you, and these computational workflows, which then make them scalable once you get them to work.
Yeah. Definitely. I think, and also I think it also depends what you would do. I mean, I think you guys are very workflow minded. If I'm just trying to run my practice, for most people, I would say, you know what, build, buy, rent, train, get trained on, or get software that's a workflow, and that's it. You don't need to know anything beyond that, maybe, And then I would personally, I don't know if you guys would do that or not. And if it gets complicated, hire somebody who's better than you at that one thing. This is what I still do, but hire that one really great designer, that one modeler, or that one person that's really, really specialized.
Yeah, and there's people now who are specializing in building computational workflows to achieve these things, and you can get a custom machine sometimes, but you probably don't need to. It's probably just more like working with the machines available. But getting people to help you make a workflow, I think, is a very wise investment if you find the right person. And we're seeing more of these consulting firms start to emerge. There's more in Europe right now than there is in the US, but it's starting to evolve as part of the palette of options for people.
Yeah, definitely. And the other example is this. I mean, if you are if you make devices a lot, if you're one of those people that is inventing a new type of liner or a new type of finger all the time, okay, then I think you might want to look at some kind of way of either learning CAD or hiring some of the knows CAD, or to really take a deeper dive in there. If you really want to invent, not make unique insoles all the time, because you can do that with a workflow. But if you need to invent something that no one else in the world has ever made, then I think CAD may be the answer, maybe a hurdle you're going to have to take sooner or later.
Yeah, so knowing how to design is a great skill to have, and having a desktop machine just nearby to do iteration, even if it's not in the final material and process, you can learn a lot from just having access to a printer and just scoping out ideas and seeing how things fit together and how things work. There's so much to learn that you can't learn from seeing stuff on the screen, because apparently scale exists. Units are important, and the way something holds in your hand is very different to how it looks on screen.
So I got a little bit of a story on the design side of things. So a friend of mine, I was actually on a call with him, and there was a specific wrist unit for an above or below elbow amputee that I didn't have, but I didn't also have I didn't have the file for, but I didn't have the actual model to reverse. He had a set of calipers, and I'm literally on the phone with him 15 minutes maybe, and he takes the measurements and tells me the whole pattern, where things are. I draw it up. I send him for a test fitting. And literally within an hour and a half, we have 5 or 6 different iterations, and we find one that works. And we were just kind of taken aback by that, because years ago, that wasn't even possible. That would be a long time process. And the cool thing is now that file stays forever. So when somebody needs that wrist, then we've got it, and we can adapt it into a workflow.
Yeah, the speed of iteration is pretty, compared to other manufacturing processes, is mind-blowing. It's what got me excited about in the first place, is just this. And the communication is geometry. as I backtrack on what I said about 3MF. But you don't have to tell someone how to do every aspect of manufacturing it. So if you're doing something out of sheet metal, you've got to get someone to cut it, someone to finish it, someone to fold it, someone to weld it. And each step of that way, you've got someone's expertise, but also their inertia of whether they want to do it for you and how much we get paid and how long it's going to take. And if they've got something more interesting to do. If you're doing something one-off, then getting that into a workflow is expensive and maybe not prioritized as someone who's making thousands of something. So it's just a very, very liberating way to solve problems very, very quickly.
Yeah, I totally agree with this. I think, I think it's wonderful. I think there's a lot of food for thought here, but I think we're all minded of the fact that, like, do deepen yourself in the workflow, reach out to experts, and do find out what's going on in the world, because technology is changing very quickly, and then you can really ride those waves or kind of miss it. That's, I think, the general feeling here. And I hope you guys thought it was great. We thought it was great. So thank you so much for being here, Duann.
Yeah, thank you. This is super interesting, and I'll see you all at some event somewhere sometime.
Maybe Rapid, maybe Forum Next. We will see, or maybe some OMP related event.
Yeah,
we will see. We will see. And Brent, thanks for being here as well.
Oh, this was great, and thank you, Duann, for sharing the insight. And I think our listeners are going to get a lot out of that, and you might actually get some O&P people shooting you some emails or what have you on the 3MF stuff, because I think it's important, even specifically for our field, as we move forward.
Yeah, all the information on 3MF is at 3mf.io, and there's a contact form there if you want to reach out. If you've got a philosophical question, I can answer for you. If you've got a technical question, I can refer you to one of the technical members. And there's also we use AI. Okay, so we're super advanced. We have a GPT, so you can ask questions about the spec. So if you want to build your own workflow, there's information about how to do that using ChatGPT. You can query the 3MF GPT thanks to Mark Burhop, who developed this, so that we can sort of give people quick, easy information on how they can implement 3MF, either as a consumer or as a producer, to make it easier for you.
Okay, super cool stuff. All right, everybody, thank you so much for listening to this episode, and we hope you enjoy this, and have a great day.
Hey, thanks for tuning in, and a special thanks to Limgard and Advanced 3D for sponsoring this episode. If you enjoyed it, don't forget to like, subscribe, and share it with your friends. And if you feel so inclined, please leave us a review. Your feedback helps us improve and reach more listeners. Have a great day.